So how is the plasma pH kept within a narrow range as we constantly produce acid? Well, to fully understand how this occurs, we must first understand where the acid comes from and the differences between volatile and non-volatile acids, which will determine how these acids are buffered and eliminated. The majority of acid comes from the metabolism of carbohydrates, fats, and amino acids, while a small portion comes from the consumption of acidic foods. Let's focus on the production of acid by metabolism. The metabolism of carbohydrates, fats, amino acids, and other compounds leads to the production of either volatile or non-volatile acid. Volatile acid is produced from carbon dioxide, while non-volatile acids or fixed acids are produced from anything other than carbon dioxide. Now, by itself, carbon dioxide is not an acid, since it does not have a hydrogen ion to donate. However, when carbon dioxide is dissolved in water, it can form carbonic acid, which can donate a hydrogen ion. Normally, the formation of carbonic acid from carbon dioxide and water occurs slowly, while the dissociation of carbonic acid into hydrogen and bicarbonate ions occurs rapidly. But because the formation of carbonic acid from carbon dioxide and water is physiologically important, our bodies use an enzyme called carbonic anhydrase to speed up this part of the reaction. This means that as carbon dioxide is generated from the metabolism of neutral carbohydrates and fats, it would quickly combine with water to form carbonic acid, which would lead to the donation of a hydrogen ion and the lowering of the plasma pH. To avoid the formation of excess carbonic acid, carbon dioxide is constantly eliminated by the lungs through normal respiration. On average, 15,000 millimoles of carbon dioxide are generated each day, while an equal amount is eliminated by the lungs. So what do you think would happen to the plasma pH if lung function was reduced, like that seen in patients with chronic lung disease? Well, it can lead to the increased formation of carbonic acid, which would lead to a decrease in plasma pH. This condition is referred to as respiratory acidosis. Conversely, increases in respiratory rate, like that seen in hyperventilation, can lead to a decrease in carbonic acid, which would lead to an increase in plasma pH. This is referred to as respiratory alkalosis. Let's now turn our attention to the non-volatile or fixed acids. Now, the average person produces 70 millimoles of non-volatile acid each day. 20 comes from the diet, 10 are excreted as bicarbonate, and 40 are generated from the metabolism of sulfur-containing amino acids, phosphorus-containing compounds, and the incomplete metabolism of carbohydrates and fats. So, how does the body handle the fixed acid load? Well, this part can get a little complex, so let's make it easy by addressing it one concept at a time. Let's start with the first concept. The daily load of non-volatile acid is buffered with an equal amount of bicarbonate, which is generated by the kidneys. This is called de novo synthesis of bicarbonate. Interestingly, changes in the non-volatile acid load are matched by changes in the bicarbonate synthesis. To maintain the plasma bicarbonate concentration at 24 millimoles per liter, nearly all of the filtered bicarbonate is reabsorbed by the kidneys. Now, although bicarbonate reabsorption and de novo generation of bicarbonate occur by different mechanisms, they share some similarities. The non-volatile acids are eliminated by the kidneys through the secretion of hydrogen ions, which occurs by different mechanisms along different parts of the nephron, and it's partially dependent on the activity of the enzyme carbonic anhydrase. Much of the secretion of hydrogen ions is coupled to the reabsorption of bicarbonate and de novo synthesis of bicarbonate. The secreted hydrogen ions are buffered prior to being excreted in the urine by bases that are filtered and generated by the kidney. Over the course of the next few lessons, we'll address each one of these concepts in greater detail and provide a lesson that puts it all together.